Welcome to module 8 lecture 4. So, we looked into carbonation and chloride and initiation of corrosion, that is depassivation by these two agents in the last lecture. Today, we will look into, and also in the beginning in the previous lecture before the last, we looked into corrosion, introduction to corrosion. We also explained that what it is actually an electrochemical process and all that. So, we will follow up from there more about corrosion today. So, what we will do is we will look at corrosion potential, because it is an electrochemical process. We will look at kinetics and effect and protection. You see, if you recollect, we talked about there will be anode and cathode formation within the metal. So, if this is my metal, if this is my metal, if this is my metal, this is my metal. So, there will be some place where there will be anode formation. So, let us say this is my anode and this is my cathode. So, in anode Fe goes out into the solution, Fe dissolves to Fe plus plus and 2 electron. Now, electron moves along this direction to the cathode and reacts with oxygen and water forming hydroxyl ion, and Fe goes into solution, reacts with this hydroxyl ion forming FeOH2, etc., etc. So, you have anode and the cathode. Now, since the electron is moving along this direction, since if I call the, and we talked about there is a double layer, there is a potential at the metal and potential at the electrolyte. There are two potentials we talked about. Let us denote them by phi. So, phi m a is the potential in the metal at anode, that means I am talking of this potential phi m a, and phi m a must be less than phi m c, must be less than phi m c. Why? Because electron is moving along this direction, electron is moving along this direction. So, phi m c must be greater than phi m a, where phi stands for the potential at the metal, right. So, we said that there is a variation of the potential from the metal surface to the solution, and we talked about 2-3 models, Helmholtz, and finally Stern's model and all that. So, we talked about. So, we are talking of the potential here, and since electron moves from here to here, so this potential must be more than this potential. So, phi m c is greater than phi m a, and if you come here, the positive ion moves along this direction. In other words, phi electrolyte A at the anode must be greater than phi electrolyte at the cathode. So, potential here at the anode is less than potential at the cathode, and if you come to the electrolyte, potential at the anode is greater than potential at the cathode, So, electrolyte potential at the is because Fe ion is moving along this direction, electron is moving along this direction. So, now if I subtract the potential phi m a minus phi E a, that is at the anode itself, let me just draw it again, at anode itself, let me just write it, at the anode itself, find out the potential difference, phi metal anode minus phi electrolyte anode. Now, phi metal anode, this is one potential, and other potential is phi metal cathode minus phi electrolyte cathode. So, if I consider these two potential, now phi metal cathode was greater than phi metal anode. So, this is greater than this, 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 and I am subtracting this is, and this is greater than this, and this is greater than this. So, you see phi, this is greater than, this is greater, this is bigger than, this is bigger than this, this is bigger than this. So, this is greater than, this is greater than this, and this is smaller than this. So, I am subtracting a larger value from a smaller value, larger value then a smaller value, and here from a larger value to a smaller value. So, I am subtracting larger value from a smaller value and subtracting here smaller value from a larger value. So, in other words, what I can say is this will be greater than the phi m a minus phi E a. The difference in potential at the anode between the metal and the electrode will be less than that in cathode. That is what we are trying to say, that is what we are trying to say, this is what we are trying to say, and we define this as electrode potential. So, what is electrode potential? Phi m minus phi E, that is electrode potential, and we have seen that E a is less than E c, E a as less than E c, because that is shown by this expression, that is shown by this expression, that is shown by this expression. Phi m a minus phi E a is less than phi m c minus phi m phi E c. So, phi m a minus phi E a is less than phi m c minus phi E c. So, electrode potential which is E a is less than E c, E a is less than E c. So, E a is less than E c. So, electrode potential at the anode is smaller than is lower than electrode potential at. So, that is what we call as electrode potential. It is the difference between the potential of the metal minus and the electrolyte at any electrode. Now, how do I measure that? I cannot directly measure this, I can only indirectly measure it. I cannot directly measure this potential between the electrolyte and the metal. It is impossible to measure this. At the interface, potential difference is difficult to measure. So, what we do? We measure it indirectly and using some external electrode, some reference electrode. Now, the potential of the reference electrode that is taken as 0 is hydrogen electrode. So, a hydrogen electrode is one which has got a platinized platinum, and you pass hydrogen in distilled water, hydrogen pass hydrogen at 1 atmosphere pressure and at unit activity, concentration of hydrogen is unity, potential is 0 and is standard hydrogen potential. So, standard hydrogen potential is measured under a standard condition when you have got a platinized electrode in hydrogen situation, which is concentration or activity being 1 and at atmospheric pressure, that is called standard hydrogen potential, and we call it as 0. So, the reaction is H2 gets broken down into H plus 2 electron. So, this is a kind of an this H2 breaks down into 2H plus ion, hydrogen ion plus electrode, and corresponding to this reaction the potential is taken to be 0. All other potentials are measured with respect to this. For example, the most commonly used one for reinforced concrete is copper sulphate electrode, and for this the copper sulphate electrode, this value is 0.32 volt with respect to standard hydrogen electrode, 320 millivolt minus 320 millivolt minus 320 millivolt. So, hydrogen electrode is considered 0, copper electrode is minus 320 millivolt or minus 32 volt. So, if you measure with respect to copper sulphate reference electrode, then you want to express it in hydrogen electrode terms, you have to make this kind of difference, addition or subtraction as required, right. So, copper minus 2 electrode, of course, it will be plus. So, if it is the direction is this copper to copper minus 2 electron is, then it will, I will call it plus 32 volt, and if it is copper breaking down to copper and 2 electron. So, I will call it minus 32 volt, right, depends upon which side is the electrons are, right. So, for concrete system, the ASTM H76, this gives you a reference electrode, copper sulphate reference electrode, copper sulphate reference electrode, where you have a wetted sponge here. This is saturated copper sulphate solution, this is a copper rod, Cu rod, copper rod connected to a high resistance voltmeter, and one point is connected to the rebar, exposed rebar. This is your reinforcement bar, and this is the concrete. This must be wet enough. So, the potential between this point and this reference electrode is measured by this voltmeter, and this is the half cell, this we call it half cell potential, because this is the half cell. The other cell is formed by the rebar and the electrolyte here concrete pore solution. And if this potential measured is less than minus 350 millivolt less than minus 350, the chance of corrosion is 90%, according to their empirical observations in chloride ridden concrete in So, they found it, if it is more negative than minus 350 millivolt, chance of corrosion is 90% of the time. But if it is between 250 and 350 millivolt, minus 350, minus 250 to minus 350 millivolt, there will be 50% chance. That means, it may be corroded or it may not be. And if it is less than, more positive than minus 250, more positive than minus 250, E is more positive than minus 250, then chance of corrosion is only 10%. So, by doing a survey over an actual site, one can actually demarcate the areas of high risk active corrosion and low risk active corrosion using this. However, this is also used for laboratory measurement as well. Now, what is the basis of this? So we got to look a little bit of thermodynamics and talk in terms of potentials which comes. Now, you see the reaction takes place, actually here electrochemical reactions are taking place. So, reaction takes place, and in the reaction what takes part is the free energy. Now, what is free energy? Some energy will be bound with the entropy, and that is not available for reaction, right. So, if some energy goes in changing the entropy, that will not be bound for available for reaction. So, if it is only isothermal process, there will be no internal energy, there will be, because it is only temperature is not changing. So, there is no change in internal energy, right, of the system as long as it is in same temperature. But chemical reaction, if it is occurring, internal energy of the species reactants and the products could be different, but some of this difference can be consumed, it might go in changing the entropy. So, remaining energy is what we call as free energy, but more important for us this is, and this is available for an isothermal process, that is for our reaction. But what is more important for us is when it is same pressure, the free energy that is available. Now, it is the enthalpy, because it is the total internal energy, total heat content of the body, which can change. So, delta H, it could be the change, but delta H will not be responsible or will not be contributing towards the reaction, because some of the energy will be associated with entropy change from, we know from thermodynamics. So, G is called free energy and it is H minus T s. This is energy associated with entropy, this is energy associated with entropy, and this free energy is what takes part in what it is exchanged in, or what influences the reaction process, chemical or electrochemical reaction process. So, if I have n moles of A reacting with B moles of B, and the product form is n C moles of C and n D moles of D, this is the kind of reaction that is occurring, then delta G, there is a change in the Gibbs free energy, that is G products minus G reactants, that governs whether the reaction will progress or not. For example, if this is high and this is low, so this will be negative, and in that case the reaction can proceed spontaneously. But if this is high, this is low, you have to supply that energy. So, one can write delta G in this manner, because free energy per mole is known. So, N C G C one can write in this manner, N C G C minus N D G D, etcetera, etcetera. And at standard reference condition, we call it delta G 0, which will be N C G C at the standard 0 stands for standard reference condition of possibly 1, concentrations are 1, etcetera, etcetera. Under standard condition, it will be given like this. So, therefore, one can write, if for a given species, let us say L species like A here B, N L G L minus G 0, it can be shown that it is actually N L R T ln by A L. A L is the activity, or it can be replaced by concentration in most of the cases. many cases ideal laws are followed by concentration, where real cases activity would be a better situation. All right. So, but we will replace this by concentration, and you can understand this because since the constant pressure situation. So, constant pressure situation, the volume change will take place. So, P dV is the work done would be, and one can write P as RT by V, and when you integrate it you will get ln B2 by B1 etcetera etcetera, and 1 by V can be expressed in terms of concentration, and for that is why it comes RT ln this way. So, from chemical thermodynamics one can derive this. I think we will not go into this derivation, but what we will be interested in, delta G products minus G reactants can be written, for this expression it can be written like this. Delta G can be written as delta G0 RT ln, concentrations activities are replaced by concentration, and they would be written in this manner like we did from here, right, like we said for here it can be, and this can be in fact written as RT ln concentration of species L to the power NL. So, for any species. So, for A, B, C, D I can write 4 such equations, GL minus G0 or delta G minus delta G0. So, I can write for delta G minus delta G0, and rest all, since I have replaced the activity by concentration, I can write it like this. Now, this was actually free energy, and this can be written using Faraday's law for charge transfer, where charge is involved. You remember the potential is basically the energy on one charge, and if I have Z is the number of electron transfer that takes place, or the valency of that species that is taking part in an electrochemical reaction, F is the number of coulombs charge associated with 1 gram mole, this is associated with 1 mole, this G is associated with 1 mole. So, Z multiplied by F will be the total charge associated with 1 mole, and E is the potential for unit charge. So, E multiplied by E is the potential, is the energy actually work done for unit charge. So, multiplied by the total charge can be related to delta G. So, when I am dealing with charges it will be ZFE. So, this reaction can be written if Z electron is involved in the electrochemical reaction, this reaction can be written as ZFE is equals to minus ZFE is equals to ZFE E0, where E0 is something analogous to Z this, or equivalent to this is ZFE 0, and this concentration still remains same because electron concentration one need not take. So, one would get by dividing by ZF all the sides, RT by ZF, you get what is called Nernst equation. So, what it shows is the electrode potential where there is a charge transfer is taking place. In an electrochemical reaction, charge transfer takes place. The electrode potential can be written in terms of standard electrode potential, that is electrode potential under standard condition, and can be expressed in terms of the concentration of the species involved in the reaction. For example, if I have like R is equals to F equals to and temperature R T, because it was a R T divided by Z F, right. So, 2.3 because it was ln can be converted into log, so it will be 2.303 RT by F is 0.59, and I can write the expression as E 0.059 Z this. And for hydrogen, of course, case of hydrogen we can write this, because we know hydrogen this value is 0, E 0 is 0 standard, because we take it to be 0 under standard condition, that is 1 atmospheric condition, unit concentration and so on and so forth. And for any other hydrogen ion concentration, the electrode potential will be given by this, where this is the hydrogen ion concentration and this is the pressure or related to activity and all that. So, for concentration or pressure being unity, this will be SH will be 0. For various other reactions, these values are available. I just want to make one point. For example, lithium, this is negative, but if you come to gold, AU stands for gold, it is 1.498 positive, silver it is positive, platinum it is positive, which means that so as long as it is negative, the reaction will occur spontaneously or it will occur, but if it is positive it will not. So, noble metals have got their electrode potential positive, they do not form a node. The dissolution of this reaction do not take place there readily, while in case of other ions such as Fe, this reaction would occur, it would act as anode. So, you connect Fe with gold, Fe will automatically become anode and gold will be cathode. Similarly, platinum, anyone on this side of hydrogen, if you connect to anyone on this side, they will tend to be cathode, and the one more negative than hydrogen would tend to be anode. And this is important in sacrificial anode selection and all that. For typical cathodic reaction in case of Fe ion corrosion, this is plus 401. So, one can actually calculate this ones for various reactions, For example, this reaction Fe dissolved into Fe, that is the iron dissolution at anode. This reaction one can find out E, and it would one would write it like this, the Fe ion, log of Fe ion concentration or activity of Fe ion will play a role. And if I put Fe ion concentration as 10 to the power minus 6, I will get it E as a constant, and this is essentially this line. So, E is constant if I put some concentration values of Fe, because this is concentration, this will relate to concentration 2.303 etcetera. We have already written 0.0, if you come to this equation 0.059 by 2 or 0.059 by 2 here, in case of iron reaction, because Fe dissolves into Fe plus 2 electron. So, you put here 2, it will be 0.03, and here the Fe ion concentration will be there. So, if you put Fe ion concentration as 10 to the power minus 6, 10 to the power minus 6 moles per liter, you will get this line, So, if the concentration is more than this, it means the corrosion is occurring. If it is less than this, the corrosion is not occurring. So, one can identify theoretically zone of immunity and zone of corrosion. Similarly, for various other reactions, one can get these curves, and which product is stable, that one can find out using Nernst equation. This diagram is called Pourbaix diagram. Now, if you look at this line, this is actually this line is for oxygen evolution. So, the equation here this line corresponds to this reaction, this line corresponds to this reaction. Water oxygen forms for cathodic reaction 4 hydroxyl ion, this line for cathodic reaction. All right. Now, if you calculate out pH, OH can be replaced, OH ion concentration can be replaced by pH actually, because we know the concentration of, when you write down the Nernst equation for this, I will have concentration of hydroxyl ion. So, concentration of hydroxyl ion, that is OH, can be replaced by, this can be replaced by concentration of hydrogen ion, and I know the log hydrogen ion, negative of log hydrogen ion concentration is pH. So, pH can be replaced by 14 minus pOH, or in other words pOH, because this will be log of hydrogen ion concentration and negative of log of hydroxyl ion concentration, that can be written in pH terms. So, you can see that it is linearly varying with pH, E is equals to E0, 0.9 pH. So, there are similarly many other, for various other reactions you can get pH varying equations. For example, this reaction, which can be a cathodic reaction under certain condition, hydrogen evolution reaction, for this you get this line, this dotted line, bottom line A. For this reaction you get B. So, you get actually equation related to pH. So, it varies with pH, linear equation with pH. So, various other reactions similarly, which are function of where hydrogen ion concentration or hydroxyl ion concentration is involved, you can get equations, and this diagram is called Pourbaix diagram, given by Pourbaix. Here in this zone, iron concentration is very little and thought to be immune zone. In this zone, iron concentration is relatively high, and he arbitrarily choose this value. If it is more than that, this is corrosion, where this ion is stable. In this zone, this specification Fe3O4 is stable, and so on and so forth. So, zones of pH and potential combination, where various products are stable, or possible product formation that can take place, is shown from can be seen from Pourbaix diagram. So, it shows that at high pHs values, high pH values you may have somewhere around these values, depending upon the potential you might have stable passive layer formation like Fe3O4. Some other cases this may form, and some other cases low pH corrosion can occur, and so on and so forth. So, that is Pourbaix diagram, and that tells us and what potential and pH range, what kind of product formation can occur. Similar diagram is available for chloride also, potential pH diagram showing domains of corrosion behavior for solution containing chloride ion at some constant concentration. So, this kind of diagrams can be obtained theoretically, but you can obtain from experimental situation also. For example, when you do something called anodic polarization, that means you supply current to an electrode. We will just talk about this a little bit more later on, and you find that the corrosion proceed in the beginning, and then suddenly the current reduces. We will come back to this, we will explain this again further. So, you can have zones of active corrosion, passive situation where oxides have formed, current has got reduced. Corrosion rate is measured in terms of current, because we talked of charge transfer, Fe ion dissolving. So, when current is less, corrosion rate is less. So, suddenly corrosion current has become less because of oxide has been formed, that oxide layer has been formed, and then this is called passive zone, this is called transpassive zone, and so on and so forth. Immune zone is below this, and etcetera, etcetera. So, one can actually experimentally also determine something similar to Pourbaix diagram and verify this scenario for various concentration situation. So, experimentally determine zones of corrosion is also possible. Now, this was as far as potential is concerned. Now, when you connect, we go to the galvanic cell again. Supposing I have got copper and zinc, and you remember it is in copper sulphate solution, there is a boundary here, of course, zinc sulphate solution, and we said that their potential will differ, and when we connect them actually current will flow. If I put a resistor, if I put a resistor, now I will see there is a potential change. So, originally potential, if I measure it without this resistor, this is a high resistance voltmeter, I will find a potential difference, or potential here also I can measure with respect to some reference electrode, and here also with respect to some reference electrode, and this is the zinc potential, copper potential. When I have measured them with respect to some standard reference electrode and put them here, when I have connected them, then the potential difference between them will change, and it will become IR, the current passing through them, and IR. So, there is a change in the potential, there is a change in the potential depending upon the R, and this is IR, this. So, this is actually we call the potential here has got actually polarized, it has got changed. So, when actual current is passing, potential actually changes, because what happens, there is a electrical double layer at the boundary, and some current has to pass through that as well, and some current has to pass through that. So, finally, some loss of drop would be there as well. So, finally, the IR drop across the resistance would be much less than this difference, it will be much less than this difference, because there will be some drop across the electrical double layer, and that is why the polarization occurs. So, this IR drop across a resistance, we call it as ohmic polarization, because I have collected a resistance, this is occurring. Now, this occurs in galvanic cell, this can occur even in case of corrosion cell. It can occur when concentration of one of the reactants, reacting species is less. For example, oxygen is less, the cathodic current may not pass, and therefore, the corrosion process will become slower. So, this is called concentration polarization. If the resistivity between the media, when there is a two corrosion anode and cathode in the corrosion cell, if there is a resistance within that media is high, then the current passing would be relatively less, IR drop across the resistance will be less, right. So, the corrosion current will be controlled by this resistivity or resistance of the media, and that is actually is occurring ohmic polarization. But sometime I might apply current from outside, voltage or current from outside, and that is called activation polarization, and that is used to study actually study or measure corrosion rate, etcetera, etcetera. This activation polarization is used, but that gives us also the understanding, because the kind of polarization that would occur, that depends upon, that actually depends upon the original condition or original corrosion, that process that was going on in the corrosion cell. Now, this activation when I am applying more additional current from outside, when this ion is actually participating in oxidation or reduction reaction, it must discard any molecule, solvating molecule to which it was there. So, if it was associated with some molecule or some situation, it must discard there or get out of it and migrate through the electrode solution interface and adjust its hydration sphere as it receives or discard electron. So, either it will discard electron, supposing if it is in metal. So, metal to it goes to the solution. So, it discard all, if it is a solid solution in the metal, it discard the solvating molecule, come out of that, migrate and move to the solution now, and at if it is taking electron or giving away electron, then it must change its hydration sphere and so on and so forth, and in this process actually it needs some some energy would be needed. So, a species already in inner plane must dispatch and migrate into the bulk. So, if it is in the inner plane of the metal, it must migrate into the bulk. If it is in the already in the solution, it has to come, it must discard its solvating molecule and then get into, pass through the interface and get into the bulk metal. So, both these cases would need some energy, and this activation energy would be needed. So, energy is required for transition from one state to other. So, we call it activation energy. So, if I am supplying current, actually I am giving activation energy. So, let us say this was the energy state originally, and you have to supply some energy in order to jump from this state and come back to this state, right. So, activation is required. So, jump from lower level to this state to other state, and net current actually species it works both ways. Net current, supplied current density will be the anodic process current of anodic process minus the cathodic current. If I am supplying current in a given way, I have pushed it up. So, actually both this process will continue simultaneously, and net current will be given by ZF some constant multiplied by the concentration of oxidant, concentration of reductant. Actually first order reaction essentially this comes out from the fact that I will just come to this, I will come back to this first order reaction, molar concentration double layer. So, first order reaction actually is product flux is proportional to K into species flux, is proportional to K into species flux. So, therefore, some constant first order reaction rate is proportional to concentration of the reactant. So, that is why some K is coming in, and from Arrhenius equation one can find out this K as this relationship is there, ln is equals to ln K, this is the kind of relationship, and one can find out K is proportional to activation energy divided by RT. So, kinetic energy increase with T and activation energy is given by depicts the reactants towards the product, directs the reactants towards the product. So, anyway it is a function of temperature, and it can be shown that K is e to the power E A divided by RT. Okay. So, this is the progress of reaction, reactants has been pushed up, this jumps from that and comes to the product level. So, that is activation. Oxidant, these are the molar concentration of the oxidized and reduced reactants or reduced out layer outside double layer, outside the reduced material, outside the electrical double layer. First order reaction is proportional to K species. Therefore, rate of oxidation and rate of reduction can be written like this. So, at any metal place, both anodic and cathodic current work simultaneously, both would be working simultaneously, and net current will be the difference between these two. So, oxidation current is given by this, or reduction for this reaction, the anodic current will be like this and cathodic current will be given like this, and at equilibrium these two currents are same, therefore, no net current is passing. But if I am supplying some current, then some current should be passing through it, and this K can be replaced by, according to Arrhenius reaction, I can replace by the free energy divided by RT, which is activation energy, and for this case also I can replace this by activation energy IA, and IC can be replaced like this ZF some constant into e to the power activation energy divided by RT and BA activation energy to the power RT. Net current will be difference between these two, and one can write it like this. Net current at the electrode, if I am applying current, then it will be given by this. But delta G can be replaced by some alpha f E A, because it is some f into alpha into E A activation energy, activation potential energy can be related to the potential in this manner. Similarly, beta f E C that we have discussed earlier, and we can write it in this manner: alpha beta f E C divided by R T and alpha f E A divided by R T. In this manner we can write it. Equilibrium current density, if the equilibrium, these two will be same. So, if I call this as I 0, I will get this kind of relationship, these two will be same Z F E B. So, this will be E 0 and this will be also E 0, this will be also E 0, and then if I write I C by I 0, I C by I 0 when it is not at equilibrium, then at any other current when there is a net current flowing, So, this will be I C by I 0 can be written like this, because Z F will cancel out, it will be left with e to the power beta f E C minus E 0 and E A minus E 0. So, if I shift it from an equilibrium potential to some potential, I will give additional by giving activation energy, this sorts of a relationship will be followed. This difference is called over potential, they are called over potential. So, if I have supplied some additional current, I will actually change its activation energy and the activation potential will change. Difference between the equilibrium potential to the new potential, I call it over potential, and what I see is I C by I 0 or I A by I 0 is given by this kind of an equation. If I take log of both sides, I get what is known as Teffel's equation. So, N C I will get N nu C is nothing but over potential, nu A, this is nu C and this is nu A, and if I take ln or log of both sides, I will get some constant, I call it Teffel's constant, anodic constant, cathodic constant, and log of I C by I 0. So, these are called Teffel's curve. So, if I apply current, I will find that actually log of current versus over potential, log of current versus over potential varies linearly, because this is a linear kind. Log of cathodic and anodic potential over potential, it would actually in a single electrode, if I do that, I will get this sort of relationship. So, these are called Teffel's relationship. So, that is how I see anodic and cathodically, if I polarize, I get this sort of curve, right. So, this is activation polarization, and as I already said, concentration and activation and ohmic polarization, we have already defined them. This was activation polarization. Now, Volmar-Butler equation, of course, gives you for a single electrode the net current equation, and this is related to this. What it says is potential is now applied when we apply to the metal, the ionization rate increases and reverse reaction will reduce. So, if I apply in a given single electrode, if I try to increase the anodic current, cathodic current will reduce, and the relationship of beta and alpha will be beta is equals to 1 minus alpha. So, that is how he is, this is Volmar-Butler's equation for single electrode. But real electrode, single electrode, both anodic and cathodic reaction goes on simultaneously, and actual potential will depend upon those. But in react corrosion cell, you have actually anode and cathode, where both anodic and cathodic reaction is going simultaneously, but depending upon where it is polarized, it will act like cathode or it will act like anode, and mixed electrode situation is what is modeled for actual corrosion process. So, actual corrosion process is cathode is a mixed single electrode, anode, mixed electrode situation is talked about. Now, where it is related, this activation polarization can be used for measurement of corrosion. So, rate measurement linear polarization technique is used, where I actually perturb, apply some current from outside over a small range, where it has been observed that although it follows Teffel's relationship in the long run when I polarize, over a very short range of potential change, it follows a linear line. For example, over this range, it follows linear relationship up to this, where this follows logarithmically linear, this just directly linear, and this in this zone I can use polarization resistance, and I can use Stern-Geary equation to find out the corrosion current density. So, I cor is given by B divided by R P, where R P is called polarization resistance, which is nothing but delta E over delta I for small current. for small current applied, such that this do not change more than plus minus 20 millivolt, such that this does not change more than plus minus 20 millivolt, and B over R p beta is called Stern-Geary constant. R p is the polarization resistance, and it is given as beta A, beta C, where these are Teffel's constant which we discussed, plus beta A, beta C. So, relationship between Teffel's constant is something like this. The other technique is to get this. So, R p can be obtained by applying current, small current in an galvanostatic polarization or potentiostatic polarization method over a small current, and there are instruments available these days, of course commercial instruments are available to find out the corrosion current density even in situ, although their reliability one has to see how good they are. There are several questions related to this, but that is not a part of our discussion right now. Only I wanted to mention that corrosion rate can be found out by linear polarization technique, where you have small over potential Na, nu A or nu C within plus minus 20 millivolt, and this nu C slope of the line, Teffel's line, in this zone, in the zone where nu A, nu C do not exceed 20 millivolt, that line gives us R p, slope of that line gives R p, and I core is B over R p. B is Stern-Geary constant given by this formula. But this R p also I can find out from AC impedance spectroscopy. I can, if and in this one the electrical double layer or the interface of the bar and the surrounding is modeled as a capacitance and the polarization resistance. So, when you apply current, the polarization resistance, you are applying all DC current by the way here, all direct current. So, when you apply an alternating current, the capacitance, because there are two metals, there is an interface, it will have a capacitance, it can store the charge and release the charge. So, this has got a capacitance. So, R c is the concrete resistance. So, if this is my this is my reinforcement bar and this is my concrete surrounding, the R c is here R c, and at the interface I will have R p as well as capacitance. So, these are parallel. So, I have got actually R p, and parallel to this is the capacitance of the interface, and this is the equivalent circuit, simplest of the equivalent circuit assume. So, when we apply an AC current through this, when we apply an alternating current through this, and we vary the frequency, from this variation of frequencies we can make two kind of plots, one is called Nyquist plot, another is called Baudet plot, and from those plot again you can find out R p, you can find out R p, and then I core is B divided by R p. So, corrosion current density can be also found out from AC impedance spectroscopy as we call it, but I do not have time to discuss them really in details. Well, there are several other methods for corrosion rate measurement, in situ electrochemical methods, colostatic methods, there are several of them, electrochemical noise method, there are a number of them, but most popular is the Stern-Geary method, LPR method, and next is this, that is why I said. But if you are looking at mass loss gravimetrically, that is how much mass loss has occurred, the mass loss will be proportional to I, the current, time, atomic weight, Z and F, from Faraday's law, that is what I mean. And if I divide I by area, corrosion current density, then R, the corrosion current density per unit area. So, R will be the rate per unit area. So, it will be the kind of mass per unit depth that is going in. So, this can be shown to be R can be related to actually, it can be related to by dividing by density in micrometer per year in terms of 3.27 atomic weight of the material. Z is the number of electron transfer involved. So, in case of Fe this will be 56, this will be 2, this value will be 28, and one can find out if you measure the corrosion current density of the material in case of steel is 7.85, and therefore, one can actually find out how much is the penetration depth per micron per year, or it is also written in 10 to the power -6 inch per year, mils per year, and so on and so forth. So, these are how we express. Now, anodic polarization I was talking about, you apply current from outside, through a potentiostatic circuit, and to this this you apply current through auxiliary electrode, and this is the reference electrode, and change the measure the potential change in the reference electrode, and that is what you use in even an LPR method, but you have other lot of other arrangements, guard ring etcetera, to do take care of certain specific things. So, if you are doing a polarization over a wide range, over a long range of potential, it is actually a kind of a semi destructive or destructive test, while LPR measurement we do over a small range of potential. Anodic polarization curve that I showed earlier to identify the zones of corrosion, we do it over a large range of potential, and you get this kind of curves, potential curves. For example, you might get this sort of anodic polarization curve, cathodic polarization curve in this manner, and you can actually find out where this is your equilibrium potential, this could be your equilibrium potential. So, it is in aerated concrete is here, it is in submerged water concrete, this kind of behavior. So, one can study the behavior, and as the potential changes, how it will behave. So, if corrosion rate is increasing, some cases it might get passivated, that means if oxides are formed and then it stops, but at a very high potential actually that might get broken down and so on and so forth. So, behavior of the electrode can be studied by kinetic behavior of the electrode can be studied by anodic polarization curve. One of them I showed earlier, and it can be studied by potentiostatic studies. Let us see the effect of corrosion. General corrosion, there are two types of corrosion, pitting corrosion and general corrosion. Pitting occurs if the chloride is coming from outside. If chloride is coming from outside, chloride ingress, chloride from outside, Now, in pitting the mass loss is very severe. In pitting mass loss is very severe, rebar it loses its dimension like this. As I showed earlier in one of the slides in the previous lecture, there is a kind of mass loss would be occurring here. So, lot of mass loss, that is pitting. So, if the chloride is coming from outside, anode is localized, then it is pitting. So, pitting is local, this is local loss, and the dimension change will be very, very high. But other cases, general corrosion. So, general corrosion, mass loss is not very high, but what happens is there is an material, the corrosion product, particularly of this product red rust FeOOH, H2O, let me write it here again, FeOOH, H2O. In other words, which you can write as FeOH3 is red rust. This occupies volume much larger, higher volume than Fe. So, what happens is it occupies a large volume, and therefore, it exerts pressure to the surrounding concrete. Exert pressure, first it fills in these pores, exert pressure to the surrounding concrete, and finally cause cracking of the cover concrete. So, general corrosion results in cracking of the cover concrete, and this can happen from carbonation or chloride coming from inside ingredients. But for external chloride, sometimes you may have pitting corrosion. If one place the chloride has gone, other place it has not gone, that location pit formation will be there, and actually totally rebar or may be lost totally. This could be very dangerous in pre-stressed concrete, because if the pre-stressing wire lost its dimension, it is under stress, it may be even causing a brittle kind of failure. So, typically you can see this general corrosion, it causes first cracking in a beam, loss of mass. In case of slab, internal crack, sagging and loss of mass. And this is what practically we can see in many cases, the slab general corrosion, it is gone from internal chloride. This is a case from internal chloride, the whole steel is gone. This is another case, in case of a staircase already repaired by doing some ganiting, again cracked because of the corrosion inside. This is of course a beam gone fully. This is the sunshade gone completely. So, there are several cases one would find. How do I protect? Quality of concrete in cover concrete, elastic modulus, tensile strength and adequate cover depth are primarily required for corrosion protection, but moisture is one thing which you should keep out. So, good waterproofing, Use of blended cement improve the protection, because blended cement exhibit better resistivity of concrete. Sometimes they improve protection, even though depreciation time may not increase, may not increase in for carbonation, but still overall it might provide better kind of protection. Use of corrosion resistance rebar, like rebar with alloy such as copper, chromium, etc., in small percentage, they like there are corrosion resistance rebar. Then coating of the surface treatment of concrete, coating of rebar like epoxy coated bars, epoxy coated, fusion bonded, epoxy coated bars, corrosion inhibitor like sodium nitrite, molybdate, acrylic corrosion inhibitors. There are varieties of inhibitors which are available, but these are to be yet to be proven. There are many things are yet to be proven, but you can have something called cathodic protection, where you apply current from outside to oppose the corrosion current. That could be impressed current system or impressed current or sacrificial anode. This is used in ship, metallic ship. So, you put aluminum, which is actually anodic compared to steel, and therefore, aluminum will actually, and it is cheap, it is cheaper, waste aluminum or whatever you can use. It is costly process as such. So, aluminum will be lost, but it will protect the steel. So, that is called sacrificial anode. If you are applying some current from outside through batteries, some cases of bridges, reinforcement bar, it has been done actually. So, it is such that it actually change the potential to such a level that it is immune potential, or in others you are applying current. In that case, cathodic protection, cathodic, these are cathodic protection. So, it is impressed current system. Coating of rebar, I said coating or surface treatment, but this material, these are all costly process. So, just to conclude our discussion, resistivity of blended cement I was talking about. You see, this is a diagram showing for OPC, Portland pozzolana cement and post-end slag cement. This is kind of a relative resistivity, and you can see the least are for OPC, these are for OPC. Next one is for different water cement ratio or for admixed chloride. So, when you have added chloride from outside, right, and you have actually these ones are for other cement for different water cement ratios for situations like this. So, blended cement actually shows exhibits. So, these are for blended cement for 3 water cement ratios, for this is for at 0% chloride, this is for OPC 0.45, 0.50 and 0.55. This is for PPC 0.45, 0.50, 0.55, slag cement 0.45, 0.50, 0.55, no chloride. But if you have high chloride, resistances, this did not change much, this did not change much, but this is relative resistance change was there in PPC and PPC. So, you can see that against chloride, this blended cement performs much better. Well, carbonation, of course, initial phases it may not be same, but resistivity still is better even in case of carbonation also, because resistivity is independent of whether it is carbonated concrete or uncarbonated concrete. So, resistance, the kinetics is controlled by resistivity, because we talked of ohmic polarization and so on. So, this finishes our discussion. We can summarize. We actually discussed about potential, and in the potential we talked about Nernst equation, Pourbaix diagram, etc. Then we talked about Teffel's equation, and then we talked about effect of corrosion, effect of corrosion, we talked of effect of corrosion, we identified general corrosion and pitting corrosion. So, general corrosion and pitting. This is only with respect to reinforcement corrosion. There are many other corrosions when it comes to steel as such, like crevice corrosion, stress corrosion, cracking and so on and so forth, but with reference to corrosion, this comes with chloride, external chloride. This is generally for internal chloride and carbonation. And then we talked about protection measures. Good concrete is the first thing. I think I must have mentioned this, but I am re-mentioning it before stopping. Quality concrete and covered concrete. Elastic modulus is important. Good quality concrete is very important. Elastic modulus, because it is related to cracking, we will look at it in the next class. Tensile strength and adequate cover depth, these are very, very important. So, good concrete is very important, very important, and elastic modulus of the concrete, that is strength of the concrete, and cover depth is very, very important. Actually, quality of construction plays a big role. So, I think with this we will finish off. We will look at the corrosion a little bit in the next class, and then we will look into the general strategy for durability of concrete in the last lecture of this module. Thank you.